Everyone, once again welcome to our physics class. Hope you all are fine over there. Children, in the previous session we had discussed about Hooke's law. Which physical quantities obtained from the graph of Hooke's law? Yes, we will get an idea about the physical quantity modulus of elasticity or elastic modulus from the stress-strain graph. And as per Hooke's law, stress is proportional to strain. So the graph plotted between stress and strain will be a straight line with a slope. The slope of that stress-strain graph gives us modulus of elasticity or elastic modulus. And what is that elastic modulus? It is the ratio of stress and strain. Okay, so as you know, there are three different types of stress and strain. So, corresponding to three types of stress and strain, we can define three types of moduli of elasticity. So, today we are going to discuss the different types of moduli of elasticity. Okay. So, first we will discuss about Young's modulus. And you know, any elastic modulus will be the ratio of stress and strain. And Young's modulus will be the ratio of longitudinal stress to longitudinal strain. So it is the elastic modulus corresponding to the longitudinal stress and strain. Okay, so Young's modulus is derived from the name of the scientist who defined it. So Young is actually the name of a scientist. It is the ratio of longitudinal stress to longitudinal strain. Young's modulus is denoted by capital Y. So capital Y is the symbol for Young's modulus. And how will you express it mathematically? That means what is the equation to find out Young's modulus? The equation to find out Young's modulus is capital Y is equal to longitudinal stress by longitudinal strain. And what is longitudinal stress? Any stress can be defined as force per unit area. So instead of longitudinal stress, we can substitute its expression force by area. And longitudinal strain, what is the expression for longitudinal strain? It will be delta L by L. We had already discussed about different types of strain in our previous sessions. Okay, so the expression for longitudinal strain is delta L by L, that is change in length by original length. So what will be the expression for Young's modulus? Young's modulus Y is equal to F into L by delta L. So how will you arrive at this expression? Just rearrange this expression. You will arrive at this last expression. Okay, how? See, you know Young's modulus F is equal to Y is equal to force by area all divided by delta L by L. So it can be written as equal to force by area into, take the reciprocal of this denominator, L by delta L. That is equal to F into L by A into delta L. Okay, so here we have A into delta L. So this is Young's modulus. So Young's modulus capital Y is equal to F into L by A into delta L. This is the expression for Young's modulus. Now, if Young's modulus is more, it means to produce a small change in length, more force is required. Okay, so Young's modulus of a material, if it is more, it means if we want to produce a very small change in its length, we need to apply more force. Okay, and what is the SI unit? SI unit of Young's modulus is Newton per meter square or Pascal. Why? Because Young's modulus is longitudinal stress by longitudinal strain. For longitudinal stress, the unit is Newton per meter square or Pascal. For longitudinal strain, there is no unit. It is dimensionless. So, the unit of Young's modulus will be same as that of stress, that is Newton per meter square or Pascal. Now, metals have comparatively greater Young's modulus. because to change the length of the metals by a small amount, greater force is required. And we had already discussed, if Young's modulus is small, what does it mean? It means to produce a small change in length, more force is required. So metals is just like that. If we want to bring about a very small change in the length of a metal, we need to apply a greater force. So Young's modulus of metals are comparatively greater. Okay, so that's about Young's modulus. Now what are the applications of Young's modulus? See, in industrial construction, steel is preferred over copper. Why? Because steel is more elastic than copper. Elastic means in order to produce a small change in the length of the steel, greater force is to be applied. That is the meaning of the word elastic here. Okay. And if there is slight deformation in steel due to contraction and expansion, it will come back to its original position. It is also elasticity. Okay, so if there is slight deformation in steel due to contraction and expansion, the steel will come back to its original position. So steel is preferred over copper to construct bridges. Okay. Now next modulus of elasticity is shear modulus or modulus of rigidity. We had already studied about shearing stress or tangential stress. So shear modulus is the modulus of elasticity related to shearing, stress and strain. Okay, so shear modulus is defined as the ratio of shearing stress to shearing strain. It is also known as modulus of rigidity, and this shear modulus is denoted by capital G. So Young's modulus is denoted by capital Y. Shear modulus is denoted by capital G. Shear modulus is denoted by capital G. Its SI unit is Newton per meter square or Pascal. So for any modulus of elasticity, the SI unit will be Newton per meter square or Pascal. So that's why the unit of Young's modulus and the unit of shear modulus is Newton per meter square or Pascal. So shear modulus is defined as the ratio of shearing stress to shearing strain. Mathematically, shear modulus can be expressed as G, capital G, equal to shearing stress by shearing strain, and for any type of stress the expression is F by A. And what is the expression for shearing strain? Do you remember the expression for shearing strain? We had already discussed this in our previous class. It is delta X by L. So when you rearrange this, you will get F into L by A into delta X. So this is the expression for shearing strain, shear modulus, okay, or modulus of rigidity. By the definition of shearing strain, 1 by theta is equal to L by delta X. Therefore, G is equal to F by A theta. Okay, because in the previous slides we had already discussed theta is equal to delta X by L. So L by delta X will be 1 by theta. So here in this expression, instead of L by delta X, we can substitute 1 by theta. Then we are left with F by A theta. Okay, so this is the expression for modulus of rigidity or shear modulus. Then what is the relation between Young's modulus and shear modulus? See, shear modulus is less than Young's modulus, and the relation is shear modulus capital G is equal to Young's modulus by 3. That is, shear modulus is just 1/3 of Young's modulus, or Young's modulus is 3 times shear modulus. Okay, so shear modulus is always less than Young's modulus, and the relation is shear modulus capital G equal to Y by 3, Young's modulus by 3. Now, the last modulus of rigidity is bulk modulus. So what do you mean by bulk modulus? Yeah, we are left with volume stress and strain. So bulk modulus is the ratio of volume stress or hydraulic stress to the corresponding volume strain or hydraulic strain. Bulk modulus is denoted by capital B. Okay, and there is an expression. It's actually a different expression. Bulk modulus B is equal to minus P by delta V by V, where P is denoted as the hydraulic stress. That means hydraulic pressure, and delta V by V is hydraulic strain. You know, volume stress is denoted as F by A, and that F by A, since it is a hydraulic stress, we can consider it as a hydraulic pressure. So instead of F by A, we can substitute P, where P is the hydraulic stress or pressure and delta V by V is the hydraulic strain. Negative sign shows that the increase in pressure results in decrease in volume, isn't it? Whenever the volume decreases, pressure increases. You know that. And whenever the volume increases, pressure decreases. So there is an inverse relationship or negative relationship between pressure and volume. Hence a negative sign is there in the relation or in the expression of bulk modulus. So bulk modulus V is equal to minus P by delta V by V, where the negative sign shows that increase in pressure results in a decrease in volume. And what is its SI unit? SI unit is Newton per meter square or Pascal, PA. Okay, so the SI unit of bulk modulus is Newton per meter square or Pascal. And also this bulk modulus of solids is greater than bulk modulus of liquids, which is greater than bulk modulus of gases. So the bulk modulus is greater for solids and it is least for gases. Okay. So what do you mean by compressibility? Compressibility is another term related to bulk modulus. Compressibility is just the reciprocal of bulk modulus. Compressibility is the measure of compression of a substance. How much we can compress a given substance. That is denoted by compressibility. And compressibility is the reciprocal of bulk modulus. Mathematically, bulk modulus is B and compressibility is denoted by K. So K is equal to 1 by B. And you know the expression for B is minus P by delta V by V. So when you take the reciprocal, you will get minus 1 by P into delta V by V. Compressibility is denoted by K. And bulk modulus is greater for solids. Hence compressibility will be least for solids. So bulk modulus for gases is less. Hence compressibility for gases will be more. So gases are more compressible. Solids are least compressible. Okay. So that's all about different types of modulus of elasticity. Young's modulus, which corresponds to the longitudinal stress and strain. Shear modulus, which corresponds to the shearing stress and strain. And finally, bulk modulus, which corresponds to the hydraulic or volume stress and strain. So with this I am concluding my session. Also I am concluding this chapter. Notes of the topic and YouTube video have been uploaded. Please go through it. We will meet in the next session. Till then, take care all of you. Stay home, stay safe. Thank you.